Hello, students and lazy chemists, and welcome to today's lecture on carbon chemistry, in particular with hydrocarbons. And what we are going to be doing today is talking some of the basics of hydrocarbons, some of the nitty-gritty stuff that we need to nail down for this. And this is kind of like just an initial properties kind of day before we get into like the nitty-gritty of like the different reactions that we can do with these. Okay. So the first thing that we should know is that most hydrocarbons are going to be predominantly a carbon and hydrogen molecule, and usually they're going to make up the primary component of petroleum and natural gas. So whenever we're talking about petroleum, natural gas, or any sort of what are we going to call it? Oil-based resource or fossil fuel, we're primarily talking about hydrocarbons. Okay. Now, hydrocarbons predominantly formed from sea creatures buried in mud during the Carboniferous. Okay. So they were organic, they were living things at one point. They get buried, they get isolated down in there, and because of their complex carbon structures, they end up forming these hydrocarbon structures when they do end up breaking down, provided that they are isolated and alone and, set there for millions and millions of years. Okay. A majority of the hydrocarbons that we are mining up right now in terms of our oil and natural gas resources, we believe to have come from the Carboniferous period. And in fact, it's one of those periods of pre-Earth history where it's named because we end up seeing that we have so much, such a source of those fossil fuels. The original source of the fossil fuels was so large back then that we ended up calling this entire period of history the Carboniferous, and this is where it all comes from. The first kind of hydrocarbon that we're going to be working with is going to be known as alkanes. These are known as saturated hydrocarbons, and it's one of those things that when you hear of things like a saturated fat, this also kind of goes into the same category. And saturated hydrocarbons are going to be hydrocarbons that are completely filled up with hydrogens. And as a consequence of that, they all end up having an Sp3 hybridization going on. Okay? So just as a reminder that Sp3 hybridization is when you end up having 4 distinct bonding groups around a molecule. You have the S bond and 3 p orbitals that are hybridizing to make 4 somewhat equal bonds around a molecule. Okay? So if they're saturated hydrocarbons, they're known as alkanes. They're Sp3 hybridized. And in general, most alkanes are going to have a fairly similar formula, where it's going to be C to some number, H to 2 times that number plus 2. Okay? And the idea is that if it's an alkane, it's going to have 2 hydrogens for every single carbon, and then it's going to have 2 extra ones on the end carbon. So butane, which is the one molecule that we have right here, is a great example. We have 4 carbons, so that means that we would have 8 from the base and then 2 on the end. And if you look at the formula for butane, it is C4H10. Okay, so an example question that I might see on this is, which one of these molecules would, have the formula of C4H10, and you could easily see based off of the names that they provide if it's going to be an alkane or not, because it's going to fall into that 2n plus 2 hydrogen scenario. The only exception for the alkanes would be what's known as cyclohexanes. Okay, and cyclohexanes are going to be hexanes or alkanes that have folded back in on themselves to make a circle. They still end up having Sp3 hybridization, but they're going to end up losing 2 hydrogens because two of the carbons are going to bond together, N carbons will bond together, and then we'll end up losing that one hydrogen. One thing that you should note is that I would like you to take note of is that the stability of the smaller cyclohexanes is going to be a lot less than the larger hexane, the larger cycloalkanes. And the reason is just that bond to rigidity, that kind of rigidness of the bond increases along this one, that just trying to bend it over there is just kind of like a real strain on the bonds itself. Whereas with cyclohexane, the angle of the bonds, there isn't quite as much of a strain. So that one is a lot more stable than cyclopropane. Okay. The next really big thing that we like to talk about is the weight of these hydrocarbons and how we distill them out. This is using typically fractional distillation. And fractional distillation is going to go ahead and use evaporation and boiling point to go ahead and separate out petroleum. Often petroleum is going to be a mix of a whole bunch of these different compounds, and we want to go ahead and get them out. So what we end up doing is that we'll go ahead and take crude oil, and we're going to go ahead and we heat the crude oil. And what happens when we heat the crude oil is that different molecules are going to heat up, and it's going to separate based off of weight and size. Okay, most of these are hydrocarbons. Okay, so they all have the same types of intermolecular forces involved, and it's mainly just London dispersion forces that are involved in all of these. Since it's only London dispersion forces, it's only going to be the size of the molecules that determines when they how quickly they can go ahead and bond out. Our heavier things, we end up using those to make roads and roofing. Larger things, we'll use those for some sort of fuel oil, okay? Usually for larger ships and central factories. Carbon chains of about 20 to 50, we'll go ahead and use those for synthetic oil, or not synthetic oil, but for lubricating oil. Diesel fuels are going to be fuels that are between 14 to 20 carbons. Paraffin oil and kerosene, which is used as jet fuel, is going to be between 10 and 16. Gasoline is going to be between 5 to 10. 5 to 9, we're going to go ahead and use those for some other kinds of chemicals. And also we'll end up using these as kind of like our precursors to plastics. And from 1 to 4, those are going to go ahead and be our gases. So for instance, methane gas and propane gas. Okay. And so the whole thing that goes on is that up here at the top, the lighter molecules are going to have an easier time getting up this column because they're going to be lighter, and they're going to be able to boil faster and quicker, whereas the heavier molecules will only be able to be retrieved from the bottom ones because they're not going to be able to travel up this column as well. Okay. Next, we're going to go ahead and talk about the combustion of hydrocarbons, and we're going to go ahead and talk about two cases of combustion. The first is complete combustion, and when hydrocarbons are able to have combustion in a well-oxygenated environment, they will fully combust, and when they combust, they're going to end up making carbon dioxide and water. Okay, so this is like our standard idea of combustion. However, if we have incomplete combustion, and this is what typically can happen in a car. So if you think like the car engine, the piston is not going to be 100% inundated with oxygen. We try and contain how much air is in that piston so that when it expands, we'll be able to get some power out of that. Since it does not have enough oxygen, what we'll find is that sometimes we have incomplete combustion. And incomplete combustion is going to end up making carbon monoxide. And carbon monoxide in and of itself is going to be a poisonous gas for us. Okay. So carbon dioxide is not poisonous to humans. However, carbon monoxide is, and carbon monoxide only happens when there's incomplete combustion. Okay. And this is something to know, especially if you are going to be going out into any kind of cold country where, or even in Florida when we have power outages. A lot of people will end up taking generators and putting them inside their house. A generator generates power via an internal combustion engine. It'll have incomplete combustion just like an internal combustion engine in a car does, and it releases carbon monoxide, which ends up, unfortunately, poisoning some of those that are inside the house there. The second thing that happens with combustion is that even though we try to get all pure gasoline and everything in here, we are going to have some nitrogen, okay? Remember, nitrogen is part of the proteins that are in the body. Therefore, we're going to have some nitrogen that's going to be in our fuel. And when that nitrogen burns, it's going to make nitric oxides. Those nitric oxides are going to be the things that form the majority of smog, and it ends up being another pollutant that we have in this environment. And an internal combustion engine is going to have two sources of that. The first is going to be nitrogen combining directly from the fuel source, and the second is because it releases so much energy to the environment, we're actually going to make some nitrous oxide just from the heat of the engine, combining nitrogen and oxygen from the air. Okay. In addition to forming smog, nitrous oxides are also going to be one of the components of, and this shouldn't be primary component, but they are also a component of acid rain. If you imagine nitric acid is a case where we have a compound where it is HNO3, and if you have a compound that's NO3 or NO2 and water passes through it, it's going to be able to go ahead and dissolve a little bit of that aerialized nitric oxide, and then it'll end up coming down as acid rain, which is something that we really don't want to end up having. Okay. This is going to go ahead and close the basics lecture for the combustion with nitric oxide for alkanes, their basic definition, their combustion, and some of the side consequences of that combustion.